here, so I'll introduce Elena Pierpaoli from USC, and she's going to tell us about this.
So I'm very pleased to be, selected to talk to you about this topic. I should mention that in this context, in the same university, there are people that are even more expert than I am, and so I will report part of our result, but also about what they have done and what they have contributed to the field. So why gravity wave and cosmology? Why do you invite a cosmologist to speak about gravity waves? Well, gravity waves may be produced in the early universe. We know for a fact that inflation, which is one of the moments in the history of the universe, very likely produced gravity waves. But because we don't know very much about the early universe in general, you may expect that there may be other processes that generate gravity waves, and these you would be able to study those looking at the large-scale structure and cosmic microwave background. And so this is why cosmology get into place. As photons come from the last scattering surface, we have that gravity waves instead can map the very, very early universe. So what is inflation? Inflation is a period in the history of time when the expansion rate of the universe was very, very high. In particular, the universe was expanding in an accelerated way back at that time. And because the acceleration is related to the density and pressure in the universe, you need to have a particular relation for that to happen. And in particular, you need to have negative pressure. So there are several evidences for inflation to have occurred in the early universe. It was a speculative idea when I started to do cosmology 10 years ago or so. But now it has several observational confirmations. And we think that this happened when the universe was dominated by a kind of energy that it was in a scalar field. Okay, let me.
I'll start. Do you mind start it again?
What?
Let me start this again.
Yeah, sure. So I made a mistake because I have a watch only on my cell phone. So if I switch off my cell phone, I'm not able to know what time is it. So either you. All right, so I have to turn around. Okay, let me shut this off.
I'll lend you my watch.
Okay, good, thanks. Because that was actually pretty stupid. People are going to call in. Basically, for this to happen, in the case of this, there is this scalar field dominating the energy density of the universe. You have some constraints on the potential and on how this field is moving within this potential. The interesting thing is that this process not only gives you some prediction on how to generate density perturbation in the universe. This process under a broad range of conditions will actually also produce gravity waves. So this is what I will try to talk to you about. There are basically three ways that you can look for gravity waves in the cosmic microwave background radiation. One is that the gravity wave produce an anisotropy at very large scale, and then the gravity wave also produce a particular unique polarization pattern in the cosmic microwave background radiation. And then there is a sort of another way of constraining it, which we put a constraint on a year ago, which is just simply the argument that if gravity waves are there, small-scale gravity waves contribute to the energy density of the universe, and the CMB is now good enough to be able to put stringent limits on the total energy density that you can have in relativistic particle, massless particle. Okay, so let's start from the polarization part. How do you get polarization? Well, polarization, typically in the CMB, you get polarization because there is, at some time in the history of the universe, there is scattering between the photons, the CMB photons, and the free electrons. So this happens at the last scattering surface when matter and radiation decouples, and it happens again at a later time when first stars and quasars start to light up and they reionize the universe. So in order for polarization to show up, however, you need the fact that the electron must see a quadrupole structure around it. So the input radiation may not be polarized, but if the scattering electron sees a quadrupole structure around it, then the observed radiation from your point of view is then polarized. Okay. So how do you get this quadrupole structure? Well, if you have just density, okay, so you can have basically three types of perturbations in the universe. You can have scalar perturbation, which are typically associated with density fluctuation. You can have vector perturbation, which are associated with vorticity, and we don't care much about them because in fact it can be shown that even if they are generated in the early universe, they decay away, so they don't persist. So we don't look for them. And then there are tensor perturbation, which are the ones that are associated with gravity waves. Now, if you have scalar perturbation, you have a density wave and you have the photons that sort of move perpendicular to the direction of the wave, then you do generate a quadrupole structure which has a particular symmetry property. If you look at it, from here, it has a very specific property. However, if you have a gravity wave, the gravity wave can be oriented in any direction, and so it stretches space-time with no specific symmetry property with respect to your original wave, and so that ends up in generating a kind of polarization through Thomson scattering that has a very peculiar signature. In particular, what cosmologists do is that they use this kind of decomposition for the polarization pattern. You see, which is called the EB decomposition. So E modes are the ones that are totally symmetric, and they are unchanged under parity, and these can be created by tensor perturbation and scalar perturbation. But B modes, which are instead not symmetric, if you flip the image, this can only be created by tensor perturbation and not by scalar perturbation. Therefore, you understand immediately that the B mode polarization would represent a unique way of actually characterizing gravitational waves from the CMB.
Can I ask a quick question? So you said in the context of the previous slide that the scalar and the vector perturbations decay away and the tensor ones remain?
No. The scalar remain there. It's only the vector ones that... No, the scalar remain there. They are density.
Scalar, that's us.
Yeah.
Okay, so what decays away and what doesn't?
The vector perturbation, if you evaluate the growth rate for vector perturbation, they decay away. And, that was worked out well before I started to do cosmology. So actually, probably I never did the calculation myself. So this is the typical pattern that you may find when you look at a piece of the sky and you try to decompose it in E and B modes. Maybe these are simulations. You may be familiar with the kind of blobby structure that you see in the CMB maps. And so these are still blobby structures, and however, there is the direction of polarization. Oops. That changes if you consider E on B. So let me come back to here. So as I said, you can get E mode both from tensor and scalar. If you had vector perturbation, they would produce also B mode, but because they decay away, we don't expect to see them. Okay, so apart from the map, how do we then describe this perturbation? Well, it turns out that a lot of the properties of the CMB can be summarized in what we call the power spectrum. So if you assume that you have a map of an isotropy, or equivalently you can have also a polarization map of the CMB. And then you expand it in spherical harmonics, which are a little bit more complicated for the E and B modes, but conceptually it's the same kind of game. Then you take the power spectrum of it, and this is what you find out. So you have temperature perturbation. All of you probably have seen this a million times. And then you can have a correlation between temperature and polarization. And then you have the polarization signal, which is typically lower than the temperature signal. And that's why it took so much longer to be discovered. So the first CMB polarization detection was by Daisy in 2003, while the first the CMB anisotropy detection was CoBe, right? So it took 10 years more to discover it. So here is some kind of complicated anatomy of all these spectra. What I wanted to remind you, though, is that the E-mode polarization are generated by scalar modes. So somehow, because you see scalar modes with a certain amplitude here, you can you sort of knew where was the level of the E modes, more or less. While the B modes are not necessarily produced by the scalar perturbation, by just the density perturbation, and therefore they could be more or less wherever, right? They could even not be there.
So how accurately are they able to predict the spectrum of the E mode polarization, just knowing the temperature anisotropy?
Well, so more or less the polarization. Well, I think pretty accurately in this part of the spectrum. Let me tell you about, because you see, okay, so the tensor perturbation will produce more or less the same amount of E mode and B mode, okay? So clearly the majority of this is still coming from the scalar perturbation, therefore, pretty accurately. But the thing that was not known is this part here of the spectrum. So this bump that you see here, and that turns out to be very useful for detection, is caused by the reionization at late times. So this is not produced at the last scattering surface, a redshift of 1,000. This is produced at much lower redshift. And they are complaining. Never mind. Shall I shut it off? Well, on, off. Here we go. All right. So basically, the amplitude of this peak was unknown because before basically WMAP, we knew that the universe is ionized up to redshift 6 from the quasars, but we didn't know precisely when, how much before redshift 6 it actually got reionized. And this bump here, the amplitude of this bump is proportional to the optical depth squared. So that's pretty sensitive to when the universe gets reionized. So, and it's actually played a big role in the current determination of cosmological parameter, because WMAP was able to detect this peak. Okay, so let me point out something else. I told you, well, the B modes are a unique way of characterizing the gravitational waves. That's true. However, there is a component of the B mode that is generated out of lensing effect of the E mode polarization. So if you have, E mode polarization generated at the last scattering surface, but then you have some intervening matter in between, the lensing effect is able to convert some of this E mode into B mode, in particular at small scale, which is a large multiple L. So while the primordial, gravity wave amplitude sort of shifts these things up and down, and it's not expected to be very big for small scale fluctuation. However, you have this sort of regeneration of power due to the lensing of the E mode. Right. So these are the two mechanisms that are typically thought for when you think about CMB and gravity waves. The first way of having limits on the gravity waves come from actually the temperature anisotropy. If you have a tensor perturbation, you actually produce also some large-scale temperature anisotropies that would add up to the standard scalar perturbation. And so when CoBe flew, the CoBe only measured L up to, say, 20 or so. When CoBe flew, the detection that CoBe had was the sum of the two fluctuation. And then there is the polarization, which I just discussed. So just to relate this to what you may be, all of you may be more comfortable or more familiar with, this is where these constraints sit. Because it looks at CoBe to start with, and then WMAP look at very large scale, the temperature fluctuation of very large scale were able to put constraints, actually pretty tight constraints, on very low frequency gravitational waves. Okay, here the solid lines are current constraints, at least at the time this paper was written. I don't know if there is anything more right now. This is the standard argument from Big Bang nucleosynthesis that tells you that at Big Bang nucleosynthesis you cannot have much more energy density than a certain amount. Okay, so they are pretty tight, but they are actually very different from the scale. They are on scales that are very different from the ones that you are normally inspecting. So after WMAP gave the new results, the temperature power spectrum was described so precisely that it was actually possible to put a new constraint on the total gravitational wave energy density in the universe. And that follows the argument that if you have small-scale gravitational waves, once they enter the horizon, they start to oscillate, and they just contribute to the energy density of the universe as if they were radiation, basically. So the location of the peaks, so the location of the peaks in the, let me do like that, sorry, the ordering is a little bit odd. The locations of the peak in the predicted CMB power spectrum, and also the height of the peak, is pretty sensitive to that quantity. Okay. In particular, so normally we model this fact with the extra radiation energy density as if you had just more neutrinos, more massless neutrinos than what is predicted in the standard model. So in the standard scenarios, you have that recombination occurs when the universe just starts to be matter dominated. In the case you have some other extra degrees of freedom in neutrinos, what happens is that you have more radiation around, and so the universe remains radiation dominated for a longer time. And so recombination actually occurs when you are in radiation dominated regime. So that changes a little bit things. And so before WMAP, the constraints that you would get out of CMB experiments was very, very weak, right? After the first year WMAP results, that became much, much tighter. And so in some ways, you can use a similar strategy to put the constraints for gravity wave, because you just model them.
Excuse me, are those massless or massive neutrinos?
No, these would be massless. It's a way of parameterizing extra relativistic energy density throughout the whole history of the universe.
I suppose now you know that the neutrinos have some mass, even though it's...
Yes, but this is just, apart from the fact that if they have some mass at this, so neutrinos have some sub-EV mass, right? So the universe here is what, 0.3 EV. Sub-EV mass. So this is about 1 EV. So they would still be relativistic here. But if they were massive, then they contribute to the total mass density at present time. So the situation would change slightly with respect to the picture that I'm giving to you. But these curves were computed just simply adding radiation, basically. You parameterize it as extra neutrinos, but you just add something that scales with a to the 4, like radiation all the time. Okay. But because you change the expansion law during recombination, and basically because of that and because of how perturbations behave, then you see that increasing this relativistic degrees of freedom changes your shapes in the power spectra quite a lot, and therefore the WMAP results were able to would allow to put a stringent limit on it. Now, what happens if you have gravitational waves? Yes, you can model them as extra relativistic energy density. There is a caveat, though. The plots that I showed you were calculated assuming that the perturbation in this component, in these neutrinos, were adiabatic with the others. And what it means is sort of that the fluctuations in the various components are in certain specific fraction one of the other. While if you don't have a specific mechanism for generating this gravitational wave background, and you don't have any particular reason for it to have any fluctuation, then you should just assume that it is there, but it doesn't have fluctuation. So in practice, what that means is that the case for gravitational waves for cosmologists results into being a mixture of what we call an adiabatic fluctuation and an isocurvature fluctuation. So it's just that your initial conditions are slightly different from what you have with the massless neutrinos. Okay, and so we inspected what difference that made, and these are the results that we found. So this was the same plot that you saw before with the WMAP or COBE, if you want, constraints down here. This was the familiar Big Bang nucleosynthesis constraint, and these are the current limit for adiabatic, if you consider adiabatic initial condition, and these are if you consider this what we call homogeneous initial condition. And you see that they actually fit on top of the Big Bang nucleosynthesis constraint. However, they extend to a much larger scale, and the reason for it is that Big Bang nucleosynthesis holds for gravity waves that are within the horizon at the time of Big Bang nucleosynthesis, while this constraint holds for gravity waves that are within the horizon at the time of recombination, and the horizon has increased meanwhile. Okay, so it extends much further. It should be said that this is very close in frequency to those ones. So, of course, this is 6 orders of magnitude smaller. So if you have any mechanism that creates sort of a flattish spectrum for gravitational waves, this gives you a much tighter constraint, right? These constraints may be interesting if you have any mechanism that create an initial power spectrum for gravity wave that is blue, that has a lot of power on small scale, but wouldn't show up at large scales. So this is more or less where we are going to go with the CMB Planck, which is the next generation CMB mission, is going to improve these constraints by more or less a factor of 5 or so. Now, in that discussion was pretty broad. Normally, when people speak about gravitational waves in a cosmological constant, they like to keep their feet on the ground, so to speak, and link to some kind of specific mechanism for generating the gravitational wave, and that is provided by inflation. So remember that during inflation, you have a scalar field that is dominating the expansion. And so you can construct some parameters, which are these parameters here, that are related to the potential and the potential derivatives. And these are the so-called low roll parameters. And what happens is that the predictions for the power spectrum in the scalar and in the tensor, for the scalar and the tensor perturbations, can be expressed as power law that contains, whose exponent contains these slow roll parameters. So this power spectrum is just as the CL that I told you before, but it's only performed in like a three-dimensional space, right? So basically, if you study the values of these parameters, you are able to then say something about inflation and how it occurred. Okay. So notice in particular, the R is the ratio between the tensor and the scalar perturbation is proportional to epsilon. Now, how can we observe inflation? Well, first of all, the amplitude of the density perturbation, of the initial density perturbation, is proportional to V. The other important aspect is that NS, the spectral index for scalar perturbation, is related to epsilon and eta, two of the slow roll parameters. Then you could look at the gravity wave power spectrum directly if you were able to detect the B mode, for example, or the gravity wave spectral index. And if you're really ambitious, you can look at statistical properties of the fluctuation and relate the non-Gaussianity of these fluctuations with epsilon. So where do we stand now? Well, as I said, COBE allowed to put some limits on the scale of inflation, and through the polarization pattern, what we know is that, well, if the scale of inflation is just a little bit lower than this value over here, then, well, maybe we will detect it. If it's a lot lower, then there is no hope. This you have seen. I just wanted then to point out that on this side there are the limits on the scale of inflation. Okay, so what did WMAP teach us? So now I will speak about what do we know, how do we know it, and what are the complications actually of this business? Well, but WMAP didn't detect the B mode. Okay, so it puts an upper limit on the B mode. It found a very nice temperature spectrum up here, and it was able to detect the E mode, especially notice this bump here, which is due to the reionization. Also, this power spectrum spectral index, NS, is determined because WMAP is able to span a large range of L values, and of course the spectral index tilts the spectrum all the way up or all the way down, and so if you have a good leverage, then you can detect it. And so WMAP was able to measure it, and one of the big news, so to speak, of the new results of WMAP is that the spectral index is close to 1, but is not equal to 1. It's they claim is statistically significant, distant from 1. And if NS were 1, you would see very likely epsilon and eta should be 0, and therefore eta is related to the tensor to scalar perturbation, so you wouldn't expect to have much tensor perturbation. Instead, because NS is different from 1, then you have eta and epsilon are supposed to be to have some values different from 1, and you can have a value of R, the tensor to scalar perturbation of the order of 0, 1. And this is big news because that means that you hope that this curve, the BB spectrum, is actually sufficiently high for future CMB experimentalists to detect it. Okay, so these are the joint contours of WMAP plus the Sloan Digital Sky Survey for R and S.
Well, how reliable is playing with N is not 1?
That's what I am sort of, this is, okay, so just one more comment, how hard can it get? Well, this is just a visual impression. So this is if the gravity waves are more or less at the present value. If you go down by more or less an order of magnitude, then you have that the lensing effect may dominate you totally. So, it's a very big issue. What is the value of R is a very big issue for experimentalists because they motivate them a lot. So now I'm going to talk about how difficult it is to be a young Italian scientist, because apart from having to learn a different language in order to do your work, you need to know basically everything in the world, right? So the argument goes as follows. So the current perspective of the present of gravitational waves depends on the scalar spectral index NS, as I told you. Okay, so as it occurs that determination of N is degenerate with the determination of the optical depth, or when reionization occurs, on which we don't have any other handle on apart from the CMB at this time. So N.
So the question, you're getting the optical depth at low L, but you determine N by looking at the range over a large range of L.
Right. So, okay. Okay. Can you wait 3 or 4 transparencies? Okay. So N itself tells you how the temperature spectrum is tilted. If N is high, then you have more power at small scale and less power at large scale. If N is low, it's the other way around. Okay. So you can get it from the ratio between the large scale power and the small scale power. However, also tau in the temperature spectrum affects that ratio, and so that's where the degeneracy comes from. So tau has another way of being determined, which is through the polarization, the low L polarization that I showed you before. So, however, the problem with that is that the polarization signal is very, very weak. And so it may be most affected. You have to dig it out from the various foregrounds and other competing signals on the sky. Not only, but also N, and the determination of N that is only based on the temperature power spectrum, so it's not affected by the polarization foreground. It is affected, it may be affected from your estimate of what is the small scale power. So this was sort of a summary of what I'm going to explain in more detail now, so don't worry if you're confused. So tau, this is the contour plots for the determination of NS and tau, the joint constraints. And I put the caption because I didn't remember all the various previous data, but this is taken from the 3-year WMAP results. You see NS and tau are very much degenerate if you cannot determine them very well. The WMAP has claimed to be able to determine tau very well, and so has somehow broken this degeneracy and have found a low value for NS. Okay. But let's have a closer look to this fact. What happens to the power spectra when you increase the value of tau? What you do is that you are erasing the perturbation, so you are suppressing power, in particular at small scales. And as you can imagine, this goes in the same direction of lowering the value of the spectral index. Okay, because if you have low value of n, you tend to have a spectrum that has low power at a small scale. Tau, however, also does another thing. It increases the power of the polarization spectra at large scale, at low L values. And this is where your constraint comes from. And in particular, the EE power spectrum, the polarization spectrum for the E mode, is proportional to tau square. So if you look at the WMAP constraints, you see that all data, if you use all the data, temperature and polarization all together, then you have a constraint that is of this kind. If you only use the EE spectrum, you basically get the same constraint. Okay? So all your constraint on tau comes from the EE, or the very great majority of it. Now, well, so far so good. You have a way of disentangling the degeneracy. However, this is the issue. Now you take the raw maps as you look at them on the sky, and you do your you look at the power spectrum. You do your spherical harmonic transform for the polarization map, and this is what you find at various frequencies. The solid lines are E mode, and dashed lines are B mode, I believe. Yes. And this is actually the analytical form for the best fit WMAP E mode that you find. So you see that you are actually getting a signal that is embedded. You are looking for fluctuations that are embedded in maps that have a much higher component. And this emission, extra emission, is due to other astrophysical objects, in particular on large scale, that is due to our galaxy. So you have to be sure that you are able to subtract the galaxy very well, in particular in polarization. And there are not very many independent measurement of the galaxy, the polarization of the galaxy on large scale at those frequencies. Okay, so this is a little bit of a concern. This is just points out how the foreground scale as a function of frequency, and that shows it better. So we have some information in temperature emission from our galaxy. Our galaxy emits at a low frequency due to synchrotron radiation, and at high frequency due to the emission of dust. And the two crosses like that, and there is a minimum around 90 gigahertz or so. Okay, so you have to guess how much the polarization emission is. And if you are able, if the polarization emission is a factor of 5 or so, or 10 below the galaxy emission, then you may be able to get to those values of R if you don't have any other instrumental noise. But certainly, there is also the fact that the galaxy, you cannot model it statistically, right? If you have an extragalactic foreground, you look at a piece of the sky, you look at it very, very well, and then you get statistical information out of it, and then you apply it to the rest of the sky. The galaxy doesn't work that way, unfortunately, and so it's a major thing to be careful about. What is the level of subtraction of foregrounds that you may get, because that changes totally the picture of how well you are going to get the B modes, especially if you are relying on the low L values as the current WMAP results. Now you think that all your troubles have finished, and in reality it's not totally the case, because now we speak about the determination of NS. As I told you, the scalar spectral index tilts the CL power spectrum up and down. And if you have point sources on the sky, these are just noise, basically. And they would show up in the CL power spectrum. They would shoot up at small scale. Now, point sources, the very bright one, you are able to observe and take away manually, one by one. But then there are fainter ones that sort of remain there in the map, and you just have to deal with it statistically. You have to imagine which kind of properties they have in terms of flux and how many they are at a certain flux, and then you model them and you subtract that signal from the small scale power of the CMB. What happened was that the initial WMAP results have overestimated the contribution of these sources at small scale. So basically they had taken away too much power at small scale, and that has caused the determination of the scalar spectral index n to be reduced for more than it should have been. So there has been a correction done from people, the postdoc at JPL, that takes away a little bit of the significance of this NS being so different from 1. And then there are also some other statistical issues that goes on a larger scale. So this is just, to sort of put you into perspective of what we need to deal with when we do this analysis, and how complicated it is, and how everything is interrelated, because you have that, the synchrotron emission of our galaxy and how dense it is, and how much power there is on a given scale. That information goes all together with how many extragalactic point sources you have at a given flux, right? And of course, all that has implication on the early universe. So, so this is, however, there are several very active people in this field, and this field is one of the trendy ones in cosmology. There have been several measurements of the polarization done up to now. There are current experiments going on that should actually give results pretty soon, these two ones. And there are several that are planned for the future. Here is a graph of the results that have been obtained on the E-mode polarization, which has been now detected by several sources. Here, there is a graph that I stole from Cholin Kuo that shows all the various measurements and where the B-mode may be sort of realistically or hopefully. This is taken from the Planck Blue Book. Planck is the next satellite that will be launched in a year and something now, that compares the prediction at the time, because this was written a little while ago, well, of the 4-year WMAP results on the EE polarization and what Planck will obtain. So you see, here you have the advantage of having a much better description of, or even of the EE power spectrum up to very high L. So you have an independent way, sort of, away from the temperature. In addition to the temperature map, you also will have a very good description of the E polarization map, which will help in constraining the parameters much better. And this is what is the expectation for the B mode. However, this was calculated after the first year WMAP results that had calculated an incredibly high optical depth. So these are sort of optimistic, because you see R is 0.1 and tau is 0.17. This is for maybe a little bit more informative. That's sort of the probability of detection of tensor to scalar modes, this R value, according to when reionization occurs. If you have reionization occurring very late at very low redshift, then you don't have such a big bump at low L, and you have low probability of detecting this the B mode signal. Instead, if you have reionization occurring very, very early, incredibly early here, then you would get a very good detection of R. The reality probably is more like this line over here, right? So Planck should get it if R is of the order of a few percent or so. So this is the summary of my talk. So there is the possibility of detecting a stochastic gravitational wave background by looking at the CMB, and you have basically three ways of doing so. One has been sort of exploited, the large-scale temperature signal, and then you have the constraints that I showed you that started to be effective when WMAP released their first-year results, and that is related to the energy density that you have in gravitational waves. And the third one, which we hope is going to be, we will be able to exploit it in the future, is related to the study of the B-mode polarization. So the current limits that you get are from the CMB on gravitational waves are very different whether you look at short wavelength gravitational wave or of a large wavelength gravitational wave. And Planck will be able to improve this result by probably a factor of 5 or so. So the fact that apparently the observed spectral index now seems to be smaller than 1, that leaves you with the hope that in fact the parameter R, the tensor to scalar ratio, is sufficiently high for future experiments to detect it. So the WMAP limit on R is of the order of 0.3, and Planck should get it if R is bigger than a few percent or so. There are other experiments like biceps that may inform us on the presence of gravitational waves in even a shorter time scale. And then I discussed a little bit how complicated it is, however, because somewhat cosmology now has become so precise, and the data analysis that is required is so sophisticated. Several aspects of astrophysics merge together, and so that's a hard job. That's it.